we're going to visualize the difference between how humans represent data, for example, -6, how the computer represents that same data, if it were a assigned integer, as a form of binary, and the location of that data. So how are we going to do this? Let's going to create a file called int specifier.c. And now we're going to vim into int specifiers. At this point, if I press tab, it will give me the entire file name. And we notice that we don't have any information here. That's what we expect. We press I in the bottom left, we see insert. And remember, we are going to print elements to the output. So first we would have our main function. We now know that void means we're not expecting any inputs. We have int here to indicate that we want to tell the operating system that the program is complete. And then we use our brace to be able to indicate the procedure. And then we want to say return 0 in order for the program. So now I'm going to say write quit, exclamation point. I'm going to do gcc-wall, so all warnings, int specifiers-c. I use tab to get the whole thing again, -o, and I'm going to say int specifiers. And I like to do that just to make sure I didn't do anything silly in the setup. If I press I know that I want to print to the output. We've learned in this reading that we need to do pound include standard io.h. And I'm going to write there. So let's create a variable. We're going to create two variables. We're going to say the int is equal to -6, and we're going to say unsigned int, the uint, is equal to 23. Now, if I were to write quit and then compile this, we're going to get two warnings. Let's quickly learn what those warnings are. They are unused variables. And that's fine. It's just telling us that we are using more memory than our program says we need because we never actually use them. So let's fix that warning by actually using them. And I'm going to do unsigned int first, just so we can go over the ideas of hexadecimal before we go into tying negative hexadecimal in with the int. So recall, we're going to do fprintf, and we're printing to the temporary file standard out. And then in the previous example, we had %u for unsigned int, and then %p for the location. And I'm going to say the uint. And then for the location, we use the ampersand, the uint. We'll write quit. We see that I have the error. I missed one of those unint. Fine, let's just go back into vim specifiers and fix that. And you'll notice as I do these videos that I compile rather regularly, so that way I don't allow several errors like this to propagate. So right now we only have one, which is unused variable, the int. And if I say in specifiers, in this time, the value is 23, and here's the specific location. We note that the operating system will change this every time, so if I do this, it's actually in a different place because the computer got rid of it, and then we compiled and put it in a new place. But now let's do the int. So we're going to go back up here, vim int specifiers, and now I'm going to do fprintf standard out. Remember, the specifier for %d and %p/n, the int, and the location of the int that we use with ampersand. We do the same thing. All the warnings are gone. That's good. And we have these values, and we see that they're close in memory. That's a good sign. That means they're both registers. They should be close. And in fact, See, 8 plus 4 is C. We have 8 is 12. And now 4 times 8 is equal to 32. Unsigned int is 32 bits. But how do we represent the hexadecimal representations here? So let's go back into vim int specifiers, and I'm going to add %x. And in between, I'm going to add the uint here. What's going to happen here is that this output specifier goes to u and represents this in the way in which people would read it, which is 23. Here it's going to print the specific location and see %p. So we're starting to learn this idea of pointers. We can represent the location in memory. But here what's going to happen is that we are going to get 23 in hex. So we have 23 minus 16, and that's going to be 7. So we have 1, 7 in base 16. So now let's run this and compile it and see how it works. It compiles, and we see that 1, 7 is here. As we predicted, 17 in hexadecimal is 23 as an unsigned integer, and we still have the location. The question is, what do we think -6 in hex would be if we did the same thing with a signed integer? Well, let's test our theory. We're going to do %x, and again, we have to make sure that there are the same number of variables and specifiers. So I'm going to compile this, and I'm going to do a deliberate compiler error to show you what the compiler error will be. You see that we have a warning. Format %x expects a different type. Warning %p expects a matching. So basically we're getting 2 warnings here, but really what's going on is that we have 3 different variables and only 2 outputs. So we only have 2 variables and 3 output specifiers. So both of these warnings are saying, hey, this pointer doesn't match with hex because it's not a data, and hey, there should be a third one over here. So that's what these 2 warnings mean. But let's go back here, and now let's add the int again. Press I, the int. We do colon, shift, WQ, exclamation point. Now before I press enter and we go back, what do we think this value is going to be? This is the hexadecimal representation of the int, which is -6. If it was +6, it would just be 6. But we now know signed integers. We have a signed bit, and 6 is 0, 1, 1, 0. We learned about 2's complement, and so we flip all the bits. This one's now going to be assigned. It becomes 1, 0, 0, 1, and then we add 1. So in this case, it's going to be 1, 0, 1, 0. And we learned in hexadecimal, this is A. So how is this represented? Well, it turns out that the rest of this is going to be all ones, which means it's going to be 1, 1, 1, 1, which we now know in hex is going to be F. Signed integers are 32 bits, which we now know are 8 bytes. So we're going to have A, and then we're going to have 7 leading Fs because we're actually going to have 28 leading ones to indicate that it's negative. Why? Because if we have for 1, 0, 1, 0, and we're trying to get the positive, we flip all of the bits, and then we add 1, and this becomes 0, 1, 1, 0 at the end, and that becomes +6. So we expect 7 Fs and then an A to print. So I press enter, compile, make sure I did everything correctly. All the warnings are now gone, and then when we print everything out, we now see that we do in fact get 7 Fs and then A for hexadecimal. So we see the difference between the value that we understand as people, how the computer represents it underneath in the binary, and where the computer represents that in binary.